Alright, so last time we talked about adsorption on surfaces. Now we're going to talk about what follows adsorption, right? The reactions on surfaces. And so again, the book uses an S as a star just to represent a site. Most literature and most other books use an asterisk like this, so that's what I'm going to use. I don't like having S. It looks like a bunch of sulfurs laying around. So essentially, A star in the book is A with a little dot S. But either way, it just means that that's adsorbed to a site. Now from last time, we were using a Langmuir isotherm to treat adsorption. And so what were some of the assumptions within that isotherm? Anybody remember any?
Bonding to one of the sites as an effect of future bonding.
Yeah, so coadsorbed species do not interact.
They only bond to one type of site.
Yeah, you can use similar things and have two site mechanisms, but generally speaking, there's one site. And then what about how many adsorbates can fit on a site? Just one, right? So one adsorbate per site. And that's why when you see the way that we write it here, we're consuming that site, right? The site, which was free, is gone. It's now attached to A. Just like we have to balance the number of hydrogen atoms, the number of carbon atoms, and even the number of electrons when we write down a reaction, we also have to balance, when dealing with surface reactions, the number of sites. Yes?
So for that last reaction, would you put a star after
Yes.
the gas?
What's the difference between what's the third one, the one site? What's that mean?
One type of site. So all the adsorbates bind essentially to the same site within that assumption. even if in reality, maybe one adsorbate binds to one site and another adsorbate binds to another site. Langmuir doesn't come equipped to deal with that. So yeah, you have to balance out the number of sites, just like you balance out the number of atoms, and even, we don't talk about it too often, but the number of electrons. So I'm also putting here just G to represent gas phase species, just to further discriminate them from the adsorbed species. But it's the same if these were coming from a liquid phase. So there are heterogeneous catalytic reactions where instead of being in contact with gas, you're in contact with a liquid. Everything would be the same here, except instead of the little g's, we would have aqueous next to those if it were in water, for example. So I write here all the steps as reversible, but often we want to assume that one of the steps is rate determining because it makes writing down the rate equation easier. So we're going to start, and we're going to come back and we're going to redo this without this assumption and just see what it looks like. But let's assume that step 3, if I number these, let's assume that the surface reaction step, which is step 3, is the rate limiting step. And hopefully you guys remember, so a little bit of review, that rate limiting does not mean slowest step, because the net rate of the first reaction is equal to the net rate of the second reaction is equal to the net rate of the third reaction. They all have the exact same net rates for this to be a valid steady state reaction mechanism. So again, we want to assume that rate 3 is rate limiting. And so what we're going to do then is write down the rate of that reaction, the net rate. So these are elementary steps, not to be confused with the overall steps. The overall reaction mechanism here would just be A plus B goes to C, right? This is not an elementary step. It doesn't tell us anything about the reaction mechanism, the number of sites it requires. Nothing is in here except stoichiometry. Here's our sequence of elementary steps. And so since it's an elementary step, what is R3 equal to, the forward rate of that reaction? K3 times the concentration of A star times the concentration of B star. And then we need to subtract from that the reverse rate, which is what?
A negative would be C star plus times C star.
Concentration of C star times the concentration of empty sites. That's fine. Empty sites have a concentration just like adsorbed sites have a concentration. So in assuming that step 3 is rate limiting, what we're also saying is that, again, this is part of the same assumption. We're going to assume that the steps which come before are quasi-equilibrated. So what do we mean by that? Hmm?
Nothing's changing with time.
It's changing with time, but it's changing so slowly that it looks like it's equilibrium.
Okay. So what can I write down? What equation can I write down to make solving this easier?
You write down the equilibrium constants.
So big K1, that's my equilibrium constant, is equal to what? Which is?
A star over A times star.
And you're essentially saying that you can use this equation because, so this equation is always true, right? But I can't substitute this equation into this equation unless what? You're either at equilibrium or quasi-equilibrated, yeah. So now we can rearrange and we can say that A star is equal to big K1 times concentration of A in the gas phase times concentration of vacant sites. Another way of thinking about this is that the rate of reaction 1 is approximately equal to the reverse rate. That's another way of saying quasi-equilibrated, right? And so if we take that to be true, then what is the difference in these two rates? 0. But I said that that was also equal to the difference in these two rates. So is my net rate 0? How can all of these things be true at the same time?
Because they're the same thing, just you said it in different ways.
No, I mean if this is true, then this is certainly true, and then my net rate is 0, so I'm not doing any chemistry. Yeah.
You're applying PSSA?
I mean, no, you don't need to apply PSSA to make this assumption, but it has to do with the sort of squiggles that I put here, yeah. No, I mean they are. They're equal to the net rate of the reaction. The net rate is the net rate. Every elementary step has to also occur at that net rate if I'm at a PSSA. Yeah?
They're only approximately equivalent. So
Right.
they're not actual.
So let's put some numbers up here, and maybe this will make more sense. Let's say that this is 100 and this is 99. So those two things are approximately equal. The difference is